All right, so, and I want to give just a quick snapshot of the rest of the semester. This week, we're going over graphs. It's going to be very similar to the last 2 weeks, where we covered linked lists in the same structure. What's the structure of a linked list applications and algorithms, and just examples and kind of just taking questions and open-ended lecture. Same thing with trees, structure of a tree, applications of trees and algorithms, and then just examples. Same thing with graphs. Today we're going to look at the structure of a graph in one algorithm very briefly, then applications of a graph, and then just examples. Specifically, we're going to see what a graph is today and how to work with it. On Wednesday, we're going to see how to use that graph for pathfinding purposes, which is our ultimate goal in the homework. We're going to use graphs to be able to do pathfinding, which will have the enemy AI being able to avoid walls and find the closest path to target the closest player while moving around all the walls. Effectively, what we'll have at the end is a full maze solver. The level isn't, doesn't have too many walls in the way, doesn't have too many barriers. But if we made an infinitely complex maze using this grid system with walls that take up blocks, your enemy AI would be able to navigate that maze, going from start to finish in the shortest path. It'll be able to follow the shortest path. That's what we're building. That's our goal for these next 2 lectures, and then just examples and kind of probably doing what we did last Friday, being more open-ended, maybe just dropping some homework 4 hints or something like that, depending on what mood I end up being in on Friday. I officially canceled lecture next Monday. I made that change to the schedule like a week ago, but I never announced it. So Monday's officially canceled. There's no labs next week. So next week, Thanksgiving break, for intensive purposes of this course, is an entire week off. As it should be, but that's a debate for a different time. We need more breaks in the fall semester. Spring's nice because we got spring break right in the middle. It breaks up the semester. It's good for our mental health and everything. Fall is just draining. It's absolutely soul-crushing. Our last break was way the hell back in week 2. It's too much. So I'll at least give you that Monday. I need that Monday too, to be honest. And then the rest of the semester, when we come back for those last 2 weeks, it's all going to be review or open-ended applications. What I like to do in these last 2 weeks is make a Piazza post where I say, what do y'all want to see? And then you can put your suggestions out there if you want. You want to talk about homework, if you want to talk about off-topic stuff. I don't care. Whatever you vote and whatever gets the most votes, within reason, I'll do during lecture. If there's applications that you want to dive into, go a little deeper in specific CSE concepts. In the past, I've taken the enemy AI project and showed you how to deploy that on an actual web server. That takes like a lecture or 2 to do that. There's a lot moving on. Or 1 lecture if I just fly right through it. But it's really up to you what you want to do with these, or just, take that time to study for your other classes, finish up homework 4, whatever you want. Of course, some of that time, of my default things, we have 6 lectures, so I got a lot I can do. I have a lot of default things that I talk about. I'll talk about the final exam, at least part of one of those lectures and things like that. If you want to go over like old homeworks, I'm hesitant to give out solutions, but I can give because they'll be recorded and people find them when I reuse that assignment. But I could verbally explain solutions. I wouldn't have a problem with that. But whatever you want to see. So start thinking about what you want to see, or if you just want a break for those 2 weeks too, that's fine too. All right, so today, graph representations. For the quiz, you have to redo the whole quiz. Quiz and interview, whatever you got wrong on it, you have to take the entire quiz or interview, which the questions you got right shouldn't be a problem because you already know how to do them. You just got to take the time to type them up. Is my stance on that. But yeah, definitely the whole thing. Which I always, let me not go down that road. Let's just get into some content. So unless anybody has questions, I'm going to go into some slides. Okay. Let's do it. So at this point in your computer science careers, you know a good handful of data structures. I got 4 of them on the slide right here. 2 of them you've talked about in 115. This is a bit much. 2 of them you talked about in 115. We have our sequential data structures. The array is what you've worked with in 115, and a key value store, either dictionaries or objects, in 115. Those you've been using for a while. You've been using them for nearly a year, depending on how your education rolled out. Nearly a year you've been working with those 2. This semester we introduced linked lists, which some of those, the underlying data structure that you used in 115 were linked lists, but you didn't have to think about it too much. But we saw the structure of a linked list, which is another sequential data structure, and also a tree, which is a nonlinear data structure, where a tree can have branching paths and have a more complex structure, have more implications, little, I'll say harder to work with when you're processing the data. All we did was traversals, but there's a lot of things we can do with trees that'll be for future classes to show you. And all those data structures help us work with different forms of data that comes in different structures itself, and then we choose the data structure which fits the structure of the data itself. So the data comes with a certain structure. For example, if we have, when we had expressions, it made sense to express that as an expression tree. We had a really convenient way to store that information in a tree structure, because it just naturally falls into the tree structure, where the root is the last operator to be evaluated, and then as we get closer to the leaves, those are the first operators to be evaluated. It makes sense to represent it that way. If we just have a list of things and the order is important, it makes sense to store it in either an array or a list. And if we have key values that we have to associate, we have some YouTube ID which maps to a song, it makes sense to use a key value store for that, a map in Scala. So let's look at another type of data. A couple examples here. This one is the one we'll be looking at most of this lecture. This is the very early days of the internet. I believe it was ARPANET at this point, at the point of this image, where the whole internet was just a handful of nodes at mostly universities, and those nodes were connected to each other. They could communicate with each other, the very early spawnings of the internet. We have a subway system, where we have stations connected by rails. Here we had servers connected by cables. Or we can have intersections connected by roads. We have this kind of structure where it doesn't really fit well into the data structures that we already have. How would we represent this type of information in any one of these 4 data structures? There's no clear winner that this is the one we should be using to be able to represent this data. But let's try one. I'll try a tree. Seems like it makes sense. We have these kind of nodes that are connected to each other. Kind of makes sense to use a tree, so let's give it a shot. So I'm going to try to use a tree. I'm going to pick a starting node just so I have a place to, where's my UCLA? Right there. Just so I have a place to start writing down my data into this structure. So I'm going to start at UCLA, and I'm going to take all of the connections from UCLA and have those all be child nodes of UCLA. So I write all those nodes down. UCLA is a node with a whole list of children, and these are going to be all the child nodes, references to new nodes with values and more references. Then I'm going to visit each one of these nodes, like Stanford, and I'm going to visit each of its neighboring nodes and have those as children of that node, and I'm going to keep going through each node and continuously add all the connections as child nodes to that node. And I got a big oops here. I have UCLA in this graph, in this tree twice. I got multiple data, and in fact, if I keep going down this, UCLA is going to have 4 more children, one of them being Stanford, which will have UCLA as a child. If I'm not careful about how I do this, I'm going to have an infinitely sized tree, and it's just going to be a mess working with the data in the tree. Oh no, I didn't update I fixed this typo. I thought I fixed it. Maybe I downloaded these slides before I fixed it. It should say children. So a tree isn't quite working out for us, but it's close. It's kind of doing what we want it to do for a little bit. So let's try again. Let's do the tree again, except now every time we explore a node a second time or multiple time, instead of adding a new reference, we're going to add a link to the existing node, which should already be there. So instead of adding that duplicate, we're just going to say, okay, Stanford and UCLA, they already have what we're going to end up calling an edge between them. So let's just say we're good with that. We'll drop the whole tree idea. UCLA had Stanford as a child. Stanford also has UCLA as a child, but I don't know, that terminology gets weird. So we're going to end up calling that an edge. We're going to say they're already connected through some link, so we're not going to add UCLA again. Then we're going to go through this whole data, all of the data in our set, and we're going to say whenever we see a duplicate node, just don't add it, but we're going to add all the new ones. And we have a few things here. We got rid of the duplicates, so that's good. But we have what we call cycles in this structure. And this is what we're going to end up calling our graph. Of course, this is graph week. It's going to end up being a graph. So this is our graph. And what we have are cycles. So we can travel from one node back to itself with no backtracking. So if I go from UCLA, Stanford, to SRI, back to UCLA, that's a cycle, which is never allowed in trees. Because if we allow cycles in trees, our recursion is going to go infinite. So our recursion in trees, our traversals, are going to make the recursive call on the child nodes, and then those child nodes will make recursive calls. Like UCLA will make recursive calls on all four of these children. Stanford is going to make a recursive call of SRI. SRI is going to make a recursive call on UCLA, and the others. And UCLA will make recursive calls back. We're going to get stuck in these cycles and get stuck in infinite recursion, which of course is going to blow everything up. If it's either going to overflow our stack or just run infinitely forever. If we have tail recursion, it's just going to run forever. Our program will never end, and we're just going to be stuck. We can't do anything with that. So since our algorithms, our tree traversals, don't work, which are the only real algorithms that we saw with trees, since our traversals don't work, we have to throw those away. We can't really use any linked list algorithms. We have to throw all that away and start from scratch and say, if we have graphs, we need new algorithms to work with this structure. Before we can really talk about that, we have to talk about how we're going to even represent this data. How do we even store this data structure? How do we even store a graph in memory? We could have nodes like we had with references to all of its neighbor nodes, which aren't necessarily children anymore because there's no real sense of like the root of a graph, for example. So we could do that maybe, but it's going to be hard to work with if we go down that road. So what we're going to end up doing is storing the nodes and edges separately. So we're going to have a data structure which remembers every single node in the graph, and a data structure which stores every edge in the graph, which are the connections between nodes. So there's no sense of parent and child node anymore. It's just here's all the nodes, and here's all the edges, where an edge is defined by the two nodes on either side of that edge. So like this edge right here is defined by its endpoints SDC and RAND. That's the edge connecting those two nodes. So nodes are the data elements, just like we've seen nodes in linked lists and trees. These are the things that store the actual data that we're concerned with. And then edges, connection between any two nodes in the graph. So there are a few different ways we can represent this. When you get to CSE 250, I think is the first time we see it in the current curriculum. You'll see two different ways. Adjacency matrix, which is a 2x2 grid, n by n, and it either has a 0 in a cell. It either has a 0 in the cell if the two, I don't feel like I'm explaining that right, where the x and y axes are both the nodes in the graph, and there's a 1 if in the cell of the cross between two nodes if there's an edge connecting them, and a 0 otherwise. So that's an adjacency matrix. You'll see that in, I believe, 250. If not, 331, you'll definitely see it for sure. The other option is an adjacency list. We're not going to talk about adjacency matrices in this class. We're going to talk about adjacency lists, which is the other option, which is often more efficient anyway, for sparse graphs especially. I got to define that now. A sparse graph is a graph where most of the possible edges are non-existent. So for example, UCLA could be connected to any other node. It's only connected to 4 out of all the possibilities. So this graph is fairly sparse. So an adjacency list, we're going to say for each node, to represent all of the edges for that node, we're going to store all of the nodes, references to all of the nodes to which it's connected by an edge. So UCLA is connected to Stanford, SRI, UCSB, and RAND through an edge. It's connected to all of those nodes. So for UCLA, we're going to store those 4 nodes in the adjacency list for that node. Stanford is connected to UCLA and SRI through edges. So for Stanford, we're going to store UCLA and SRI. SRI connected to UCLA, Stanford, UCSB, Utah. So we're going to store those 4 nodes under SRI. So we have this data structure which is going to store for each node all of the nodes that are connected to that node via an edge. This is our adjacency list. And in the code, this is what our graph is going to look like. So in the code, we're going to represent a graph, we're actually going to start combining those data structures, those 4 data structures that we know. We're going to start combining those to be able to represent all of this information. So, and as a little logistical note, we're going to give each node a unique integer ID. So all of our algorithms that we write for our graph are going to work on integers. It's going to work on the integers assigned to each node. So when we add nodes to this graph, we're going to assign each one an integer value which is unique to that node. We're going to store all the nodes in a map which maps its unique ID to whatever that node actually represents. And then our adjacency list is going to work with those ints. We're not going to work with anything of type A. The only time we work with anything of type A is when we need to go to that node map and say, hey, I got this ID, it's an int. Can you tell me what value is actually associated with this thing? And then that map will say, oh yeah, it's this thing of type A. So everything else is going to be an int. The adjacency list is going to be a map of ints, the IDs representing the nodes, to a list of ints, the IDs representing that node's neighbors. So we have a map of int to list of int. So we take our key value store and our sequential list and combine them to represent this adjacency list. And that's how we represent all the edges in the graph. And then our map of nodes is going to store every node in the graph. So we have a nice combination of data structures, a map and a map of ints to list of ints. By combining the data structures that we already know, we can build a new, fairly more complex, a little bit more complex data structure. And this is true for a lot of CSE 250 when you learn about all kinds of different data structures. try to think about this, be a little careful when I say this, but we've pretty much exhausted the new, like brand new, fundamentally new data structures that you're going to see. I might be forgetting one. I'm trying to think. But sequential, array list, linked list. You'll talk about like doubly linked lists and different types of linked lists. Key value stores, trees and and trees. Beyond that, there's not like new novel data structures. The rest you're going to see are combinations and different applications of the data structures that we know, that you already know. Like a hash table being an array, which is kind of used as a key value store, but the indices are the keys. But like a hash map is just an array. It can be an array of lists and combine them that way to handle hash. I'm getting beyond the scope of this. But we have the data structures that you're going to see, and then we're going to combine them. So graph, we're just taking data structures that we know, and we're using them in a new novel way to build a more complex data structure, a graph data structure, which uses the data structures that you know as their underlying, as the underlying representation of this new data structure. If we want to add a node, we're going to give it a unique index and the value that we want to store, add it to our nodes, and add it to our adjacency list with an empty list. And then when we want to add an edge between two nodes, we're going to do it by indices, and we're going to add it to both adjacency lists. If we're adding an edge, index 1 and index 2, these two nodes are connected. We need to update the adjacency list for index 1 and index 2. We're going to pull the current list and prepend, well, it's prepend because it's more efficient, prepend the other end of that edge to these adjacency lists. So with an adjacency list, we do actually have duplicate data. If that's something you're concerned about, you can think about how to get rid of that. But there is duplicate data. Every edge is represented in this adjacency list twice, which is true for adjacency matrices as well. And technically, if we want to get technical about it, there are actually two edges. There's actually no duplication. Edges are inherently unidirectional. You can only travel an edge one direction. So by adding both edges, we're saying we can travel both ways on this edge. So it's actually not redundant, but it's more of a nuanced point. Because this is an undirected graph. But again, I'm getting a little too off the rails on that one. Yeah, the IDs are like primary keys. So if you're storing this in a database, the IDs will be your primary keys for these values. And we need the IDs to be unique because they're the keys in this map, which have to be unique. If we have duplicate IDs, we're going to have collisions in that map, and we're going to get data overwritten. Whatever the last node you added to your map was, that's the one that's actually going to be in the graph. So the IDs have to be unique. For your homework, what we're eventually going to do is build the level. The game board is going to be a graph. So you have to have a way to map a specific grid location with an XY value to a one-dimensional int, which I actually have a function in the, I think I call it make graph method. But in there, I have a function which will do exactly that. If you just want to steal that function, use that in your code, it's going to match exactly the way the graph was made in my helper method, which is, I think, takes the x value, multiplies it by, takes the y value, multiplies it by the width of the game board, and then adds the x value. It'll end up giving you unique values, I think. I might have said that a little wrong, but you can get unique values. You can map 2D values to 1D values with just a little bit of algebra. Yeah, it'll overwrite the original. So if you call add node twice with the same index, whatever the second one you added was, that's the one that's going to stick. So if you, like this right here, where you're adding a key value pair to a map, if you add with the same index, an index that's already in the map, it overwrites whatever's in the map at that index. It always overwrites. Which was handy in genetic algorithm when you have a map. If you take my hint and have a map of YouTube IDs as strings to songs, and you update a song, you have a new song object with the new rating added that you just processed, just throw it in the map. It's going to overwrite the old song. You don't have to worry about that old song. You don't have to remove it from the map or anything. You don't have to do any of that. Just add it to the map. It's going to overwrite because they have the same key, which is the YouTube ID, which are unique. So same theory here. If you accidentally have multiple indices, not all of your data is going to be represented in that map. So some nodes won't be in your final graph if you're using this implementation. I mean, and also feel free to not use, like I have my graph and my breadth first search algorithm that we'll end up seeing in the repo. If you don't want to use either of those implementations, I ain't forcing you. You don't have to. You can use something else and solve these things in a different way if you want, where you can have duplicate IDs or no IDs at all. I ain't forcing you to do anything. But if you're using my code, the IDs have to be unique. And then to use this, we'll create a new graph. I'm just going to represent each one of these nodes as strings. Create a new graph of string in this case. Give each node a unique ID. I just started at 0 and incremented until I had all my nodes. Add all my nodes to the graph. And then add all the edges to the graph as well. So wherever there's an edge between two of these nodes, like there's an edge between UCLA and Stanford, I'm going to add that edge by ID to say UCLA 0 and Stanford 1 are linked by an edge. And you can count on seeing some code like this on your quiz for LO4. You'll see something like this where I create a graph, throw some nodes and edges in there, and then start asking you questions about it, about the graph. Everyone feeling okay about this? After we made it through the code, through the structure? And this is what a graph is. All right, let's keep going. So let's define another term. There are a lot of, as with any new topic, there's a lot of vocab that comes along with this. Nodes we're already good with, but edges and now paths. Path through the graph is a sequence of nodes that are all connected by edges, where each adjacent pair of nodes is connected by an edge, I should say. So for example, UCLA to SRI, Utah, MIT, BBN, RAND is a path in the graph because whenever I went from one node to the next node, there was an edge connecting them. As a counterexample, SRI, oh my goodness, I'm blind. There it is. SRI to Utah to BBN is not a valid path in this graph because there's no edge between Utah and BBN. So this is the idea of a path. And the length of a path is the number of edges in the path, or rather the number of nodes minus 1. So if this is your path, you have a list. You would take the length of this list and subtract 1. That's the length of that path. So let's talk about breadth first search with that idea of path in our heads. So breadth first search, which I think I've spelled right, breadth first search. I had a whole bunch of slides. I hope I don't have one today. I might, though, where I call it breadth first search without the D. So let's define one more term before we get into that. Connected component means that there exists any grouping of nodes such that all those nodes, any two nodes in that grouping, have a path between them. There exists a path between them. So for example, this graph is what we call fully connected, because the connected component, a connected component of this graph is the entire graph itself, or rather there is only one connected component. All nodes are connected to each other because there exists a path between any two nodes in this graph. If that were not the case, if we remove two edges here, now this graph is no longer connected. There are pairs of nodes which cannot, where there is no path between them. So for example, this graph has two connected components. Now this connected component here, and then this connected component here. And you can't get from one to the other. So the first thing we want to do with breadth first search, we'll eventually use it for pathfinding purposes. What we initially want to do is say, how can we tell if two nodes are connected by a path? So we're going to start, which for this one we can just look at it. If I ask you, are UCLA and BBN connected? You would say no, just because you would use your eyeballs, look around, and say, nah, they're not connected. But what happens when the graph is much bigger? So this was the internet, back in the day. But the internet's grown just a little bit since then. And this is a graph of the internet, I think probably a decade or two ago by now. But the internet's gotten a lot bigger. If I ask you, are two nodes of this in this graph connected? Is this node right here connected to this node right here? Like, can I get from those two servers? Can those two servers communicate with each other? Are they connected via the internet? You can't just look at this graph and decide. You can't just say, oh yeah, look, there's the path. There's one of the paths right there. And say, yeah, they're connected. So we're going to need some algorithms. We're going to need some computing power to help us solve this. So let's write an algorithm. Breadth. Oh, yep, there it is. There's my typo. Breadth first search. BFS, I'll call it. BFS, we're going to start at some node and continuously explore all the connected nodes. Are connected by an edge. So I'm going to choose UCLA as my starting node. And I'm going to repeatedly explore all of what we call the neighbors, but all the nodes that are connected by an edge to any of the nodes that we've explored. So we explore some starting node, explore all of its neighbors. All the neighbors that we just explored, we're going to explore all of their neighbors. And we're going to continuously do that, continuously expanding our search by traveling all available edges, all edges that cross this boundary of this box that I'm drawing. So these two edges cross that boundary, we're going to explore them. And then once we hit a point where no new nodes are added in one of these iterations, we're no longer expanding, then we stop. We're done. It's BFS in a nutshell. And we have to have a little logic in here to make sure that we never visit a node twice. We want to visit every node at most once, or else we're going to go infinite. If we keep revisiting nodes, it's potential to blow things up. So if, it's 2 slides ahead, but I want to say it now. If you start at a particular node and you explore another particular node while you're running BFS, then those two nodes are connected. When BFS finishes, you have the set of explored nodes is the connected component to the node that you started with. That's one of the connected components of this graph. All right, now it's time to hit you with some code. This is in the repo. You have this. You will have to modify this for your homework, but I do give you a starter BFS just because I don't know, kind of don't want to make you go through implementing it this late in the semester. You've been through enough with, especially homeworks 2 and 3. But BFS, but you will have to modify this. I swear I get this question in office hours at least 10 times every semester. Somebody cut and pastes my BFS and doesn't change it at all and says, why doesn't it solve the lecture tasks 5 and 6 for me? Well, because you still have to do something. I mean, I'm giving you a huge starting point, but you still got to do something. So, you do have to modify this. What I would do is gut this, take this code, and forget about the inputs, and then change the inputs and output to suit your needs. For example, this returns unit. It drives me nuts when students call this method and say, it returns unit. What am I supposed to do? Yeah, it returns unit. It doesn't do everything for you. It's just meant to be an example for you to build off of. So build off of this when you're working. So let's step through this a little bit. We're going to start with a set of explored nodes, and we're going to use a queue, which I'm going to use an actual queue instead of a list, just because I think it's fun to show you an example of a queue. So I'm going to actually use the queue class. We're going to use a queue, which is going to track the order in which we're going to explore nodes. So I'm going to initialize things by taking my starting node, saying that we already explored that, so don't explore it again. This set, oh, I forgot I used a set here. A set is going to, and this doesn't need to be a set. A set's, what's a very brief, it's like a set from CSE 191. It doesn't allow duplicates, is its big feature. It doesn't allow duplicates. So this dot contains, and usually these are built off of trees. I could use a tree right here. So this doesn't allow duplicates. I'm going to add my starting ID in queue. I actually check for that anyway, though, so I don't really need a set. But it is efficient, but anyway. And we're going to add the starting ID to our queue, and then we're going to iterate through our queue. We're going to keep pulling the first element from this queue. We're going to dequeue from the queue until it's empty. When the queue's empty, we know we're done. If the queue's not empty, we're going to dequeue and get our next node where we're going to explore the neighbors of that node. So we're going to go to our adjacency list, get all of the neighbors of the node we're exploring, and here's our crucial check. If that node is not explored, so if it's already explored, don't do anything. If it's already in our set, don't do anything. If it's not explored, we're going to explore it. We'll give some printout just so we can know that the thing's working, because this returns unit and doesn't really do anything. So I'm just going to print something just so I can see it working. We're going to mark that node as explored. Oops. We're going to mark that node as explored. Here's the syntax to add a value to a set. And we're going to enqueue that node to mark it and say, hey, when this gets to the front of the queue, explore all of the neighbors of this node that haven't already been explored. So we're starting at the start node, and then in this queue, we're keeping track of all the nodes we're going to explore the neighbors of. And each time we explore a node, we're going to mark it as explored. Every time we add a node to that queue, we don't want duplicates in the queue. Every time we add a node to that queue, we're going to mark it as explored so we do not add it to the queue again. So every node gets added to the queue at most once. If the whole graph is connected, we're going to add every node to that queue once and explore all of the neighbors that have not already been explored. In fact, if you use it's not part of the course, but if you use a stack here instead of a queue, you get depth first search, DFS, with a little bit of extra modification. So for connectivity, start at node. If you have a question, or this used to be a lecture question, it's not anymore. If you have a question that says, are node A and node B connected? You choose one of the nodes. Let's choose node A. Run breadth first search with that as the start node. And if node B is ever explored during the run of that algorithm, then you know they're connected. So we can programmatically tell if two nodes are connected without having to stare at a graph and try to map out all the paths and everything. We're just going to throw it at our CPU and let the CPU do the work. So what we love doing is, it's computer scientists. We're going to let the hardware do the work for us. And computer engineers would just let the hardware do it for us. If I hit it enough times, maybe I'll find another slide. Anybody have any questions? Thought I had one more slide about BFS. On Wednesday, we talk about BFS applications in depth. That's where we finally get to the pathfinding. Any questions? How is DFS different from BFS? So BFS has, so you can kind of see this as it's hard to explain. I just want to say it's kind of got a breadth to the search. How you're kind of expanding through this graph in a very wide way. Depth first search would instead visit one of the children, then visit a child of that child, then visit a child of that child, or a neighbor of that neighbor, a neighbor of that neighbor, a neighbor of that neighbor, and then go back and explore anything that was missed. In this case, you're going to get, you might get a path like that. Or say you went this way and explored SRI first, you might go to Utah, SDC, RAND, UCSB, and then go back and then visit Stanford at the end. So it gives you a different order in which you explore nodes. And most importantly for our homework, DFS you can't use for pathfinding. It won't find the shortest path. But BFS gives us nice properties as we're exploring the nodes that we will be able to exploit to be able to find shortest paths while avoiding any walls in our game. DFS just doesn't give us that property. I find DFS, there are fewer applications, useful applications of DFS than BFS. Yeah, let's get out of here. See everyone Wednesday.